Okay, guys, we are moving into algebra. And so we're looking at using things like x and y and solving equations with them and consolidating things that we've been doing all year into a formal representation of this algebraic concept. So we've been talking about algebra concepts all the way through the year. You'll note that in this lesson here, there's a lot of things that we've actually done together. We've talked about, I've brought up throughout the year. And so now we're just kind of really looking at it all together as one overarching concept. So to go through some definitions, we have the term variable. If you're familiar with programming at all, it's the same kind of concept. A variable is just a placeholder for a value. It's an unknown quantity. So it could be, and we've used it in an example here, if I have a right angle triangle and we have, a 7, 8, and then x. Here we have our missing value, our missing hypotenuse. That x, that's our variable. That's our unknown quantity. And then we can go about putting this into the Pythagorean theorem and solving for that unknown quantity. So that's what a variable is in one concept. Another case is that it's a quantity whose value can change. And so when we talked about linear equations, something like y equals 7x minus 2, we were able to take those variable values, which are the x and y, and change those depending on the situation. So we could make a table of values with x and y and have 0, 1, 2 as our x values. So the x value is changing and the y value would respectively change as well. We'd put the 0 in for x and we'd get y equals negative 2. We'd put the 1 in for x, we get 7 times 1 minus 2, which would give us 5. And then we'd put the 2 in for x, and in that case, that would change the y value as well, because it would be 7 times 2, which is 14, minus 2, which is 12. So the x and y values can change as well. So depending on the situation, it could change. In the case of a linear relation or relationships like that we work with, the value does change. In the case of a static representation like this, it can't change because there's only one solution that's going to work out for a right angle triangle. So depending on the case, it could change, it might not change. We usually use a letter to represent this, but we don't have to use a letter. I could go in here, I could get rid of this x, and I can change that to a smiley face, and that still works. What's the smiley face? Well, we can have our Pythagorean theorem written out, and we can have 7 squared plus 8 squared equals the smiley face squared. It doesn't matter what we actually use as long as we have some sort of symbol there. Generally, though, we will use a letter. Most commonly, we'll use letters like X. Y is another common one. Z, N. But in most cases, I'll tend to the X because that's how I was kind of trained and experienced. So that's where we're looking for those letters. All right, so now another common term that we'll use is an algebraic expression. So in the case of an algebraic expression, it's just a mathematical phrase that combines the numbers and variables with math operations. So the numbers are we just define variables, and then the math operations, things like adding, subtracting, multiplying, dividing, square roots, and all that. So something like 3 times x equals 4 would be an expression. 4x minus 6 could be an expression. 3y plus 2x could be an expression. So the different expressions are going to combine those numbers, letters with mathematical operations. Now, those expressions are made up of what are called terms. So each of those expressions is made up of terms. A term is a number, variable, or the product. Product means multiplication of a combination of the number and variables. Generally, it's separated by plus and minus signs. It's one of the easier ways to recognize it. This isn't the exclusive definition, but it is probably good for our purposes. So some examples of terms. If I have something like 4x, that's a term. It's one term because it's 4 times x, so that's a product. So this is one term. If I have something like the 4x minus 6, that is 2 terms. There's one term here, the 4x, and then the minus 6 is another term, the negative 6. So there's 2 terms here. And then in the case of something like 3 is one term. And I could have something like 4x minus y plus 7. And then in that case, we have a term here, an independent variable here, and an independent number here. That's 3 terms. So terms are just the separate portions of it, and those become important when we're trying to do some later solving, when we have things like a monomial, one term, binomial, bi meaning 2, mono meaning 1, or a trinomial kind of a terminology where we have these 3 parts. So those are important things to keep in mind, be aware of as we're working through these. So those are important terms: variable, term, and algebraic expression. So now in this topic, what we're doing is looking at how we can use the variables to represent length, area, and volume. We've, again, done stuff like this. We've mentioned this in the past. We're just kind of formalizing it. So when we see a letter like X, we can think of X representing length. It's some length we don't know. I could take a straight edge here. I'm going to cover up the measurement so we don't know and draw a line. So we don't know how long that line is. That line has a length of X. And we can then go about using the ruler to measure out and find out how long X is. So it's an unknown value, and just an X by itself could represent the length of a line. So in a couple examples of working with this, we got John stacking 12 cases of pop-up. Each case is X centimeters tall. And, it could be cases of those little mini pops. It could be, the regular 12-ounce can, or it could be like a 16-ounce can, or it could be like the big giant size cans that are like 750 liters or milliliters or 1 liter cans or whatever. So he's stacking these up. So each case, we're not sure. It's just X centimeters tall. So what's the total height of the stack? Well, if we think of X as a number, say X was 3 centimeters. The total height would be 12 times 3. But in this case, we don't have a value for X. We just have X. So X is something. There's 12 of them. We stacked up X 12 times. So our total height, in this case, equals 12 times X, or just 12X. And in this case, our units would be centimeters. So our height is 12X. And that is our single term representing height, 12 times X. And again, we don't put the times sign in there. The reason why we tend to avoid that with variables and things like that too is because we often use X, and X looks like a time sign, depending on how you write your X's. Another example, we have Sue drives X kilometers to Sudbury to pick up her cousin. They drive back to Sue's house. How far did they travel? Well, they went X kilometers all the way to Sudbury. They went X kilometers all the way back. So it's a total of X plus X kilometers, or another way to write that is 2X. So they traveled 2X kilometers. And there's our term, and then we just put the units in there in this case. So in these two situations, we don't know the actual height, we don't know the actual distance that she traveled, we just know that it was some distance. So back and forth would be 2 times that distance. 12 stacks of those cans would be 12 times that height of a can. So we can use these variables to represent situations, and this is where we get into the concept of what's called mathematical modeling. Now we can also use variables to represent concepts like area. And so if you recall back to the Pythagorean theorem, we had mentioned the concept that, x squared, when we're talking about a squared plus b squared plus c squared, we're actually talking about a square on the side of a triangle. So when we had that setup, we actually had a square on each side. We could divide that up into, this was, a square 4 by 4. And this could be a 3 by 3 square. And so those are areas. So there's a squared and b squared, and then our c squared side was a little bit bigger, and it was the sum of those two smaller squares, because we could add all those up and have the 1, 2, 3, 4, 5 squares. So not the best drawings, but this is actually a square. And when we talk about the area of something, we're actually talking about how many little squares does it make up. So whenever you see the variable squared, what you should be thinking about is it's a square of x by x. So some side length by the same side length. So in our case here, working with some examples of how we can mathematically model using this area, a concept of a variable, we have Tina wanting to carpet her hallway. So when you're going to carpet your hallway, you got to know the area of it so you can buy the right area of rug. And that's how it's usually sold. It's sold by square footage or whatnot. So in this case, she knows the length is 6 times the width. So we want to write an algebraic expression for the length. So the length of her hallway, and I'm going to use L, is 6 times the width. So if the width is, well, what's a good letter to use for width? W. So you don't have to use X. We can use any letter. We'll use W for width, and it's 6 times that. So then the length is actually 6W. The length is 6 times the width. Is how that would read out. So now if we know the length is 6W and we know the width, we're just calling the width W. So that's if the width is W. I'll write that cursor there. So if the width is W, then the length is 6 times the width. So now we want to know what the area of the hallway is. So area is length times width. So the area of her hallway, area equals the length, 6W, times the width, which is W. Well, here we have 6 times W times W. What's W times W? W times W is W squared. So 6W squared. And that will give us our square units for this. And so in this case, 6W squared would be the width of the hallway. The W squared portion here being that squared area there gives us our squared portion of a variable, which again represents the area. So if we had little squares that were W by W, the area of that square would be W squared. And we'd have 6 of those put together to make up her hallway. So maybe her hallway looks like this. 1, 2, 3. We got to make that longer. 4, 5, and 6. So there's a representation for hallway. Each of these is W squared, W squared, W squared, and so on. And so each of those little squares is W squared, and we have a visual representation. So when we say 6W squared, we're actually talking about 6 squares that are made up of W by W. Now we can expand this further into our third dimension and look at volume and representing volume with variables. So in our case here, we're looking at putting together, and I bring this concept up of using the little centicubes. So you have these little cubes that are 1 centimeter by 1 centimeter by 1 centimeter. When we're talking about x cubed, we're actually visualizing ourselves a cube that is x by x by x. And how many of those cubes make up the volume? So in the case here, we have Rick with a square base box. So he's going to have some sort of box with a square base, and then we don't know the height. So I'll just draw it here. Here's my representation of it. And so it's a square base box. So we know the length and width of the box are the same because it's a square base. So we can use a variable like x. So the length and width of the box are x by x. That'll make a square base. And then the height is 4 times the width. So if this is my length and this is my width here, it's 4 times x. And so 4 times the width is 4x. So the volume, we know, is length times width times height, right? Length times width times height. And so we can fill in those values. The length is x times the width, which is x, and the height, which is 4x. And so I'm using those mathematical dots, which is another notation for times. Again, something we avoid is using the x for times because we'd have x, 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 and it would look really messy. X times 4x. Well, are we x's or we times, and it gets confusing, so we don't write it that way. We either write it like this, or we can write the volume as x, and then in brackets x, and then in brackets 4x, like that. And in either case, you're getting the same thing. It's x times 4x. Now, it's all being multiplied together. So we have x times x, which is x squared, times 4x. And then x squared times 4x, well, x squared, we have the 4 just kind of hangs out there, and we do x squared times x, which is x cubed. We have x cubed being 3x's multiplied together. Recall that when we have anything to an exponent, what that means is it's x times x times x. It's this base times itself this many times up here. And so there's an example of working with the length, width, and volume. So again, when you're working with these variables and you're seeing things like x, well, x represents a line whose length we don't know. It's a line of length x. When we see x squared, what you should be picturing and thinking about is a square that is x by x. So the area equals x squared. And then in the case of x cubed, what you should be visualizing is a cube that is x by x by x. And so the volume of that is x cubed. So that's the kind of general concept, the kind of general image that you want to kind of put in your head when you're thinking about that, those representations. So that's some just general representations of how these work. And then you can try out some of the practice problems that are on the website.